Good day, ladies and gentlemen, and welcome to the CUAHSI Seminar Conference Call. My name is Lakeisha, and I will be your coordinator for today. At this time, all participants are in listen-only mode. We will be facilitating a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press star followed by 0, and the coordinator will be happy to assist you. I would like to turn the presentation over to Mr. John Duncan, Project Manager. Please proceed, sir.
Thanks, Lakeisha, and welcome everyone to today's Cyberseminar by Paul Brooks of University of Arizona in SAHRA, who's going to give a very exciting talk from what I can gather. And he's actually giving this in front of a live audience out there in Tucson, so it should be good. So thanks all for attending. This is the last Cyberseminar of the semester, and I'm just going to quickly go over some of the details for those who are new to this. You'll notice there's a participant screen in the upper hand right, so you can see who else is here. The chat box on the lower right. You can send messages to all participants, which is in the default drop-down box, or you can select an individual, and that's kind of like whispering in the back of the room. We're always eager to get feedback on this, both the technology, the topics, and everything else. So that could be addressed to me at commanager@cuahsi.org. And as always, this presentation can be downloaded from our website in case you run into any technical glitches. So at this point, I'd like to turn it over to Paul, who's speaking on behalf of a very broad, wide, and prestigious team. Dr. Brooks' research and teaching interests are highly interdisciplinary in nature, with a focus on watershed-scale elemental cycling, terrestrial aquatic interactions, carbon and nutrient biogeochemistry, ecosystem response to disturbance, and biogeochemistry of snow-covered systems, and I could probably keep going. Dr. Brooks is a 1995 graduate of the University of Colorado Boulder and is here to talk today about the title I'll let him describe. And Paul, I'm turning the control over to you.
Okay, am I on, John?
Yep.
All right, thank you very much. I appreciate the fact that late in the semester a number of people have shown up here, both online and a lot of people here in this room. And I want to introduce my talk slightly differently than the original title that was been bandied around for the last 6 weeks or so, which was meant to generate a little bit of interest to get more participants here late in the year. But the content of the talk really isn't going to change much at all. It's a community science facility, more along the lines of what this seminar series is supposed to be about, and more along the lines of, I think, the title that CUAHSI would want, but it's always good to stir the pot a little bit here late in the term. What I'm going to talk about today is the result of a large amount of research, a large amount of discussion through many, many people. Most of them, or many of them, are listed here. A lot of iteration of ideas over the last 6 or 7 years or so. So anything that you like in this presentation has probably been pretty well vetted through an impressive group. Anything that's miscommunicated or perhaps might be a little bit too far out on the limb, this first person here in the list will take full responsibility for it. So, the motivation behind this talk is that SAHRA's been around for 6 or 7 years, and there are a lot of parallels between what an environmental observatory will do, whether it's for CUAHSI, CLEANER, or NEON, and what a science and technology needs to do. This particular talk is an overview of a small part of the research that SAHRA's been doing for almost 7 years now, with the hope that this is useful to folks that are trying to develop, trying to define what an observatory might look like. The talk is not a sales pitch for any observatory. It's not associated with any observatory. It's not approved by anyone. It's purely the result of our experiences over the last 7 years and things that we think may or may not be important. And for those who can't wait, I'll start with the summary. And the most important one that we've come up with, the most important part of our experience, is that begin with a question. Develop a broad question, broad enough tent that will incorporate a lot of sub-disciplines within the group that you want to reach, whether it's hydrology, ecology, or engineering, and then develop the appropriate infrastructure. I think there tends to be a tendency among the groups putting together observatories to say, look at all the cool stuff that we have. Let's come work here. We can answer a lot of questions in this environment. And from NSF's standpoint, from the feedback that we've gotten over the years, and from our standpoint on what works, start with the question and then decide where you want to address it. Most of the work that I'm going to talk about today is where I live, from here in the University of Arizona. Once you get those questions, you get rapid buy-in from collaborators, people within your group, and more people coming and wanting to work with you. Progress is made very quickly. Subsidiary questions, linkages that might not have been envisioned at the beginning of the program can be developed. More research questions can be generated. You can go out and get funding for those specific research questions. And that's important to this third part. There's never enough money to accomplish everything that you want to do. There's always going to be more questions, more call for resources as the questions continue to evolve, as the research areas continue to evolve. Okay, so for the rest of the talk, now that you know what the talk is hopefully going to lead to, the points that it's going to lead to, I want to give you a brief introduction to the Science and Technology Center, SAHRA, for those of you who may not be familiar with. Talk about the integrating questions and rationale for some of those questions, how we've organized our research. Talk about some of the initial results from those studies, and then really get into the idea of this observatory, of finding a place in which to do our work, how the evolution of research and the development of field facilities and infrastructure followed after the first few years of findings, and then give you lots of data, lots of results, very preliminary results just from the last couple of years. All right, SAHRA is the Science and Technology Center for the Sustainability of Semi-Arid Hydrology and Riparian Areas. Its mission is to promote water management within, by conducting water resources research, outreach, and education within the context of what stakeholders need, critical management decisions. I'm going to focus my talk here primarily on science. This arrow here, the long arrow on the bottom, and then the small arrow pointing to our time point here, roughly midway through 2006, gives you a reference on how far along we are. So we've had a number of years of experience, and it's that experience as we go forward that we want to share. It also points out that we're a middle-aged Science and Technology Center, and that's where the title of this talk comes from. We're looking at our legacy. What are the products that we're going to put out beyond just hundreds of peer-reviewed publications, beyond simple management tools? If there's something broader that we can come up with. SAHRA's working partnership of about 300 university and laboratory personnel. Even though we have a very large budget, when you distribute it among 300 people, it doesn't go very far. But it does parallel what an observatory will need to do and bring in a wide group of people from many states and indeed international participation. We're going to have to work in any sort of observatory environment with people coming from What does SAHRA do? SAHRA does hydrology, obviously, focused on semi-arid river basins, process research, infrastructure, database development, and integrated modeling. It does that primarily within the Southwest in several main river catchments, the Upper Rio Grande, the Rio Concho, the San Pedro, and the Salton Verde. It also is tremendously successful in knowledge transfer, education, and outreach from the basin to the international scale. I'm not going to talk anything about this today. There's not going to be time. I'm going to talk primarily about process-based research and infrastructure development. All the research that I'm going to talk about today, all the research that SAHRA performs is grouped under three integrating questions, three broad questions. What are the impacts of vegetation change on basin-scale water balance? What kind of water markets and water banking are fees of riparian restoration and preservation? I like to view these as more process research, more social science research, or physical process research, social science and economic research, and then some integration of the two, where both management decisions and science are needed to be integrated into a more complete understanding of how we protect or restore these riparian systems. I'm going to focus my talk primarily on this third question, or this upper question, the third question from the left. What are the impacts of vegetation change on basin-scale water balance? The role of SAHRA science with any of those questions is to significantly improve understanding and management of water resources. We do that or we try to do that, and I think we're pretty good, by identifying and filling gaps in the scientific understanding of critical hydrologic processes, develop management tools that incorporate that understanding, and facilitate that knowledge transfer to stakeholders, to management. I think we're pretty good at that, and I think we have the ability to shortcut because we have a longer funding horizon, the typical lag that it takes to go from process research to management tools. But again, I'm going to talk primarily here on identifying and filling gaps in scientific knowledge. The critical gap that we've recognized is ecohydrology, or one of the critical gaps, which leads to the question of what are the impacts of vegetation and vegetation change on basin scale water balance. You can think of a nice hydrologic cartoon that you might all use in Hydrology 101, where you have precipitation, evaporation, transpiration, interception, soil moisture, groundwater, stream flow, surface flow, interflow, all the typical points of a hydrologic cycle that you might want to introduce. And from a physical perspective, it's nice to put these together, but when we start working in a semi-arid environment, vegetation mucks up all these physical processes, starting with interception and, of course, ET, and all the way down through stream flow and groundwater recharge. My colleague, Fred Phillips at New Mexico Tech, views this ecohydrology question or vegetation change question as the 800-pound gorilla that as hydrologists we've been ignoring, perhaps to our detriment. And it's an area that we've decided to tackle within the Science and Technology Center. Why focus on vegetation? I want to give you a quick overview on some of the reasons we focus on vegetation. This is a picture that I downloaded from the web, and I use it in my classes, and I use it in many of my talks, because it so clearly shows the difference associated with water availability, water balance, and the hydrologic cycle in vegetation. Here in the front, we have a grassland, shrubland system. Down here, we have an area of groundwater recharge or groundwater discharge in the riparian system. In the back, we have a little bit higher elevation with much denser vegetation. And then here, we have a range of hill slopes, each of these facing somewhat north, with very different types of vegetation. We look at this, and we clearly see that there are differences associated with the hydrologic cycle and vegetation. We can use those differences in vegetation perhaps to scale hydrologic properties. But if we look at these three slopes, we see that within any particular environment, there's quite a bit of variability in vegetation, suggesting that there's quite a bit of variability in the hydrology in each of these locations. And of all these aspects, topography, aspects, soils, and vegetation, vegetation is really the only factor that changes on human management timescales. Some examples of vegetation change throughout the Southwest are juniper invasion in the grasslands in New Mexico from 1899 to 1877. We're dealing with significant juniper encroachment. Here on the bottom left, shrub invasion into grasslands in the Santa Rita Mountains in Arizona. 1902, broad grasslands. 1950, a shrub grassland mosaic. And then 2003, almost complete shrubland cover. And then up in the mountains of northern New Mexico, from 1907, a fairly sparse ponderosa pine forest with a lot of grassland, and the expansion, the filling in of that forest, and the expansion of the grassland, or the expansion of the forest out into the grassland. We have examples of rapid vegetation change from beetle kill in Colorado, the Rodeo Chedesky fire in northern Arizona, obviously logging, and then the pinyon die-off, which has been a recent topic both in the news as well as in publications. A lot of work by Dave Brashears and our colleagues up in New Mexico looking at the effects of drought on the pinyon in northern New Mexico. So the approach that we've taken, or the initial approach that we've taken in addressing these questions, are to develop new process understanding of how hydrology interacts with vegetation, or how vegetation interacts with hydrology. Develop rules for scaling that, a common theme throughout observatories. How do we scale that process knowledge? And then incorporate that into a database and a modeling environment where we can actually make predictions and understanding. This is sort of a little fairly analogous to your typical 3-year NSF funding profile, but we have the opportunity to do much more integration here, and I'm going to come back to this a little bit later after we review some of our initial results. First, I want to start with the effects of vegetation on precipitation. Snow is a major player in the hydrologic cycle. It's the source of most of our ground renewable stream flow runoff. So we put a lot of effort in looking at the effects of vegetation and snow cover. This figure here on the left, if you're not familiar with it, is a binary decision tree. And each of these branches represent a statistically significant amount of water stored in the seasonal snowpack. This is for a site in Colorado, and what we see is that solar radiation is the most important player controlling the amount of water stored in the seasonal snowpack, and not elevation. But if we look at the normalized difference vegetation index, a remotely sensed index of how much vegetation is found in the catchment, we see that a large number of these differences in the amount of water in the catchment are related to the presence and the amount of vegetation. If we jump forward and now look at stream flow, this is work from Kevin Dressler. Again, this is the Rio Grande River. The solid line here is measured stream flow in the Rio Grande. The lightly dotted line, which you see falls off the measured peak, is a modeled result using remote sensing data of the snowpack. And this heavily dotted line is an improvement in that model just by incorporating a measure of remotely sensed vegetation into this product. So clearly we saw that vegetation is affecting the amount of snow, it's affecting our ability to model its runoff and stream flow. We jump on to another location now. How does vegetation affect infiltration? This is work from Eric Small and his group looking at shrublands and grasslands. We see that in a grassland environment we have relatively shallow infiltration underneath the canopy, not quite as much infiltration in the interspace between. When that environment switches to a shrubland, there's much deeper infiltration and much greater contrast between the canopy and the interspace or the bare area between. The suggestion is that this contrast results in deeper water sources, deeper water that's available only to shrublands. These water islands are intense, available during periods of drought, and further research by this group has gone on to show that indeed when you experimentally induce a drought, you see that the shrubs are able to harness water for a longer period of time and continue to respond, continue to grow. If we jump to a larger representation of this, looking at vegetation and recharge, what happens to that water after it infiltrates near a shrub or near a grassland. This is work from Michelle Walbert and Fred Phillips. It's a climatic gradient, an elevation gradient, an ecotopological gradient here across the top, from desert scrub to shrub grassland mix and juniper woodland. The y-axis here is depth in meters. These are soil cores. And the x-axis in all of these sites are chloride concentration. And what you see, if you see a peak in chloride concentration as you do in desert scrub, it means that water is infiltrating to a certain depth as liquid following rain events, and then coming back out as gas. You're not getting as water vapor. You're not getting recharge. In contrast, when you move to higher sites, juniper woodland, you don't see that peak, suggesting that there's constant recharge. Perhaps fairly low, but relatively constant low to moderate recharge. When you're in the same environment, the shift from grassland to a creosote shrubland is associated with very little recharge here in the shrubland, but again, moderate recharge in the grassland under the same environment. Follow-up work went to look, that's nice inferential data. It's not direct measurements of hydrology, so they followed this work up with Renee Sandvig and actually looked at integrated matrix potential across these different environments, from creosote to grassland to juniper and ponderosa pine. On the x-axis, the y-axis here is chloride accumulation time, how long chloride has been accumulating at a particular horizon in the soil. And here in this slide represents dynamic downward flux in the ponderosa site with very little downward flux of liquid water, very little recharge at the creosote site. Again, linking the inferential data from the chloride profiles to actual hydrologic measurement here. It also focuses our research up in these higher elevations as water sources, both for groundwater recharge as well as the stream flow that we showed in the Rio Grande a few slides ago. Jump to another location and look at what happens with shrub and grassland encroachment and runoff. Paired catchments in a historic grassland, one shrub, one that's been invaded by shrubs, and one that remains a grassland. We can look at sulfate concentration on the y-axis and chloride on the x. This square with error bars here represents the value in precipitation events. The circles represent shrubland, and the triangles here represent grassland. We see a very different pattern in runoff following precipitation events in ephemeral channels draining these sub-catchments. If we go and look at the isotope value, deuterium and O18 of water, we see that again with precipitation being the squares, runoff being the triangles. The runoff that comes from shrubland looks exactly like the water, or very, very close to water that fell. The line here is the local meteoric water line. If we go and we look at the grassland in contrast, this is the first precipitation event here, and runoff in the triangles looks like a mix between that first rainstorm and water that fell maybe 3 or 4 months previously and was stored in soils in the winter. The next rainstorm again looks like a mixture between water that fell in that rainstorm and water that was stored in the previous event, suggesting that these grassland soils are able to store water even though the infiltration is not terribly deep or as deep as it is in the shrubland, and even though energy balance of these sites suggests there should be no water stored. Finally, we'll jump to a third site. This is up on Mount Bigelow, or a fourth site or a fifth site, I forget where I am now, looking at vegetation and evapotranspiration from any flux towers. Before the monsoon, the partitioning of incoming energy shows that most incoming energy is going into sensible heat. There's very little water available, there's very little latent energy flux, which is the blue line, and the CO2 flux, the response of the ecosystem, is primarily positive, which indicates that it's respiration. There's very little carbon uptake. As soon as the rains begin, you see a close match between sensible and latent heat flux. You see a lot of water vapor moving through the system, and you see the ecosystem switch from a source of carbon to a sink of carbon, suggesting or indicating that the vegetation is turning on. And then finally, another site looking at what vegetation may be doing with incoming precipitation. This is what my colleague Dave Goodrich calls the amazing mesquite. This figure shows precipitation here on the bottom, and then sap flow in a tap route here and in a lateral route here. When the site is very dry, before rains begin, the tap route is harvesting deep water. As soon as rains begin, the tap route switches, the lateral roots turn on, and the lateral roots are starting to pull water from the superficial soils that fell in these rainstorms and pump it down to a deeper location in the soil, presumably where only the mesquite tree can get at it later in the year. So that's a quick and dirty highlight of research from many different catchments around this, many different research sites around the southwestern U.S. Conceptually linked projects all dealing with vegetation, vegetation change, and ecohydrology. Tremendous progress, great findings, many, many papers, including papers in Science and Nature, summarized very quickly. But putting this all together is hampered by the fact that we're not getting these measurements. It'd be nice to know if the runoff pattern looks the same in the sites in New Mexico as it does in Arizona. If the shrubs in New Mexico are actively pumping water to deeper depth, or is it just infiltration? It would be nice to combine these locations in a co-located research site, getting to the idea of an environmental observatory or hydrologic observatory. So if we come back and revisit this question, or revisit our objectives don't change. We still want to go from new process understanding, distributed data, and modeling, but we want to develop a research site where we have the ability to go out, move from process understanding, take that down to distributed data and modeling, but then make predictions of what we should see out in the field, go back and predict what we should see in terms of distributed data, locations where we did measure, and then go back and perhaps look for processes that we didn't necessarily incorporate into the model the first time through. The idea of pulling these together is the process knowledge, the distributed data, and the modeling all at one location, rather than simply relying on the modelers to pull disparate results from many sites together. So identifying these coordinated research sites was certainly not easy. Everybody wants to work at their own location. The location where they've been working is probably best for the type of research they want to do. They have a tremendous data set. We needed to come together. We needed to think about what it is that we could use, what it is that we wanted to find in a series of co-located research sites that would give us the most bang for the buck, would still address our integrating question, but would also be useful for the broadest range of We decided we needed a range of vegetation types in close proximity to address the vegetation change question. We wanted nested catchments as a time-honored measure of scaling hydrologic processes. We wanted collaborators and partners, folks to work with, folks to provide secure locations, folks to help us with our data collection, folks to come in and join us both as research partners as well as perhaps land managers who are interested in the results of our endeavors. We did that in two locations. One that I'm going to talk about primarily today is winter precipitation dominant with a cold continental snowpack at higher elevations that represents the areas of significant runoff and significant groundwater recharge to much of the western and southwestern U.S. And that's in the Valles, Caldera in northern New Mexico, or it's really in the Jemez River, the Jemez Mountains and the Jemez River. The other one, which is proceeding in parallel to this, is in southeastern Arizona, where we have monsoon-dominated precipitation. We have natural climate comparison between these two locations. But in the interest of time, I'm only going to be able to talk about results here from the Valles Caldera site, or the Jemez River. The site is roughly 1,450 square kilometers in the Jemez River Basin, runs from 3,400 to 1,700 meters in elevation. The Jemez Mountains in northern New Mexico here, approximately west of Los Alamos. False color topographic map here shows what our experimental design. We have intensive research sites identified by these stars where we have coordinated measurements in major vegetation types, mixed conifer forests, ponderosa pine forest, and slightly off the map here, pinyon juniper. Meteorological measurements and snow-tail sites distributed around the catchment, and then stream gauging at multiple sites, nested into a larger and larger array. This continues down into the larger catchment that I showed in the previous picture. The intensive research sites are crowned, if you will, by an eddy flux tower. We measure precipitation as rain and snow, land surface atmosphere, energy, water, carbon balance, partitioning and precipitation and infiltration, runoff, recharge with soil moisture and vadose measurements, vegetation water use, how the plants are using the water directly, and then groundwater within that. Chris Duffy has presented this fairly well as what he calls able to, conceptually at least, and hopefully in practice, close the energy and mass balance, both from the atmosphere to the land surface, from the land surface, the vadose zone, and from the vadose zone to groundwater. So we're not black boxing any particular exchange here. We're trying to get measurements in all of these areas. Associated around these sites, we have distributed data collection, which includes met stations, snow-tail sites, with more snow-tail sites going on, scintillometer measurements to get sensible and latent heat fluxes over larger areas, snow depth sensors, event-specific remote sensing, key to vegetation, and key to keep times in the hydrologic cycle for the site, soil moisture, snow surveys, groundwater, and biogeochemical sampling. Here we have a met station, intensive field campaign during the monsoon season with precipitation and soil moisture, snow surveys, and the highly calibrated forehead soil moisture sampling technique demonstrated by Eric Small. The nested catchment, of course, we have discharge, met data associated with these sites as well, groundwater levels associated with these sites to link up with our groundwater measurements near the towers, geochemical tracers, isotopic tracers to identify water sources and residence time, and then biogeochemistry to hopefully get an idea of how the ecosystem is responding to the site as well. Experimental manipulation. This is the result of having great collaborators and partners who are both land managers and research scientists themselves. We get to take advantage of that affects the hydrologic cycle. Experimental thinning of vegetation to see how that affects water use by vegetation. These are externally funded activities and highlights the need for partnerships and collaborations to take advantage of these opportunities. I want to go through now and show you some preliminary results from the site. These are hot off the press in the last year and a half or so. And we're going to follow them through, starting with our schematic, our cartoon of the hydrologic cycle from Hydrology 101, go through precipitation, interception, evaporation into soil moisture, and then eventually go down looking at groundwater and stream flow as we move through the catchment. Essentially, we're just going to follow water through the catchment. And the water's moving slowly. Okay, starting off with snowpack site. Several years of extensive snow surveys looking at physical properties have been examining how vegetation affects the magnitude of snow water input. And as a brief summary, a quick and dirty summary, under canopy has roughly 40% less water than open areas do out away from trees. That's not surprising. That's been found in a lot of locations. Canopy fringe has a little bit more water, but this is interesting. Here at these continental sites at mid-latitudes, the shaded aspects on the north side of trees have as much as 22% more sweet. We've seen the effects of shading in other studies on the timing of snowmelt, but not so clearly on the amount of snow. And this has led Keith Musselman, working with Noah Molich and myself, to put together a fairly simple model for his thesis of how vegetation shading and canopy interception combine to affect the amount of snow in a catchment. The figure here on the upper left shows incoming solar radiation and the shadow cast by the tree from 10 to 4, the time of day when solar radiation is highest, when the sun is high in the sky and the albedo of the snow surface is less important. That energy is penetrating deeper in the snowpack. So in a quick and dirty model that we've put together, or I wouldn't say quick and dirty initial result, Keith is going to defend this tomorrow. So it certainly is not a quick and dirty model. It's ready for, hopefully ready for prime time. Is Keith here? What we've come up with, or what Keith has come up with, I should say, is that looking at canopy cover here, a measure of forest density in the lower right, the x-axis here, and normalized SWE, comparing the amount of snow that would be present out in the open to the amount of SWE that's actually present in a large area due to vegetation. That as canopy cover increases up to about 60 or 65% here in early to mid-April, you're actually getting more water. You have more water accumulating in the seasonal snowpack. Once you get to this critical junction around 60 or 65%, the effects of interception tend to be more important, suggesting that having a moderately spaced forest may actually enhance the amount of snow as well as delay its melt or spread out its melt during the season. Now, if we take a look at what vegetation might be doing in response to that input, these are looking at sites in the same area, the mixed conifer site, highest elevation. Preliminary surveys looking at root counts with very strong RAU students digging 1.6 meter pits all over the hill slope. We see that in the mixed conifer site, in these areas where it looks like there's more snow out in the open, there are many more roots. We don't know, we haven't addressed the fact that these roots respond to the fact that there's more water in the open, and we haven't specifically looked at whether or not these pits are located on the north side of trees. But that's an area of research suggesting that the response of vegetation to changes in precipitation in the summer or the winter may be very different. It looks like these trees are responding to winter snow input. If we slowly now move down to a lower elevation site at the ponderosa pine, we look at infiltration and soil moisture, and now looking at the response of these sites in the summertime, where summer precipitation is a little bit more important than winter, looking at soil moisture at a range of depths. The figure here on the top left is volumetric soil moisture content from the 0 to 40 centimeter sensors. The blue line here are precipitation events. The red, the black, and the green are the canopy edge or the canopy fringe, open areas, and then areas underneath the canopy. We see that with summer rain, there's greater water input, there's greater and deeper soil water input at the canopy fringe and underneath the canopy than there is out in the open. So winter snow seems to preferentially go into the open. Winter water preferentially infiltrates in open areas. Summer precipitation preferentially infiltrates here at the canopy fringe. But curiously, there isn't a response of these trees at drier sites to the increased water input underneath the canopy or at the canopy fringe. If we move on, again very slowly.
Yeah, this is the one slide that really slowed down, but it went before. Hopefully it shall go again.
Okay, here we go.
There we go.
Now, if we look at biogeochemical markers of how much water may be available to vegetation, we can look at the delta C13 of carbon-6 during the 2004 year. This is just one quick and dirty snapshot looking at our juniper, our driest sites, our ponderosa moderately dry sites, and our spruce sites. This dotted green line is what we'd expect to see if there was if these sites were responding to patterns in water availability associated with microclimate. And instead of the sites falling across this line, spruce fall pretty closely here. But the ponderosa pine site shows no fractionation or very little enrichment at this particular location, suggesting that the trees are not closing their stomata due to water stress, that they have plenty of water available, so that we're seeing this depleted carbon in the growth ring from that year. And it suggests that they may have access to groundwater. If we jump forward and now look at groundwater levels as well as stream stage, we see that in this ponderosa pine forest, located, maybe a half a kilometer or so from these research sites, we see a diurnal cycle throughout the summer, both during the dry down from snowmelt as well as during the monsoon season, a reproducible annual cycle indicating that the trees are at groundwater supplying base flow to the stream. And as soon as the rains start here, this is precipitation across the top, the magnitude, the amplitude of this cycle, as well as the timing, not shown here, shifts slightly, suggesting that their trees are switching to using that soil moisture from these precipitation events and not using as much groundwater. So how much water is the vegetation using across these range of sites? This is evapotranspiration per leaf area. In this slide didn't come through, but the blue is mixed conifer, the green is ponderosa pine, the orange here are the juniper sites, and we see that there's a pretty good relationship between evapotranspiration and vapor pressure deficit, which is good for scaling. But the figure down here, which is somewhat complicated, and you'll have to take it on faith, because I'm not going to go through the derivation, it shows that in the drier sites, the juniper and the ponderosa pine site, the vegetation actually does respond somewhat to changes in vapor pressure. At the mixed conifer site, there's very, very little response in stomata sensitivity and the opening of stomata in response to vapor pressure deficit. All right, so that's a bunch of hot off the press snapshot of results from a lot of different subdisciplines working closely together. How do we pull this together? This is an outline of our Jemez River catchment. This is the Valles Caldera with intensive research sites, locations in here, standard measurements that we can use of water level in lakes as well as discharge in streams, all put together in a fine resolution topographic model, in this case working at 100-meter grid size, very fine resolution modeling, and using that modeling to go out and predict how much precipitation, what the evaporative fraction was, evapotranspiration components, lateral moisture, soil moisture dynamics, and groundwater fluxes at locations where perhaps we didn't measure it. So we can go out and validate how well we're doing with our spatial distribution, our scaling of data across this site. And then we put it together in a standard model where we look at hydrograph components both at the basin as well as interior stages, the response of stream flow to basin forcing. So pulling it together fairly quickly brings us back to our summary that you need to begin with questions to get on site. You need compelling questions that are broad enough to incorporate many different subdisciplines, but you need them specific enough so that people can see where their research makes a contribution down the line. Once you get the buy-in, once you get people working together, progress develops very quickly. More and more questions are being generated as we start to put these results together. And then, again, there's never enough money to do this. There's not a single result that I showed you today that was solely supported by SAHRA research. Every investigator within this group uses both SAHRA research funding as well as leverage resources to pull this together. And with that, we can take questions.
Well, Paul, thank you very much for a great talk. And I guess, Lakeisha, at this point, can you go over the instructions?
Ladies and gentlemen, if you wish to ask a question, please key star followed by 1 on your touch-tone telephone. If your question has been answered or you wish to withdraw your question, please key star followed by 2. Please press star 1 to begin. Stand by for your first question. Again, ladies and gentlemen, that's star 1 to ask a question.
You can also type a chat message if you want, so I just sent those instructions. Any questions from your audience there in Tucson, Paul?
Any questions here? We're in the event center, so it's really broad. It's hard to get up to these people way back in the cheap seats here. What, about 15, 20,000 people here? What are we?
Imagine.
There are no questions on the audio portion, sir.
Okay. So, Paul, I've got a question. You mentioned that SAHRA is a middle-aged STC. And so how do you see how your results that you've come up with, some more recently than others, are going to change what you're going to do for the rest of the life of the STC itself? Kind of the adaptive measurement strategy type question.
That's the $64,000, I guess with inflation, it's the $64 million question now. One of our first goals is clearly make sure that these results are incorporated into models and management tools that our stakeholders, the people that were responsible to develop management tools for and translate that information. That's one of our first priorities, to make sure that transfer of knowledge takes place. As far as the infrastructure and the field facilities, as we continue to move forward, we see ourselves transitioning from more of a intensive field measurement, modeling, establishment of the infrastructure to more of a synthetic approach where we have a research group that works and plays well together, and we encourage other people to join that group and move forward. Ideally, what we're putting together here in terms of infrastructure and knowledge will be useful to others as they go forward.
Sure. Okay. And can you speak a bit, I know SAHRA has been doing a lot in terms of development of methods to engage other researchers. And that's not just, you know, research is not just at the University of Arizona, research is not just in the arid Southwest. I mean, it seems like SAHRA has done a lot of great work in terms of, you know, building up to being able to have, what was the figure, over 300 folks working on this.
I think we've just been fortunate in having a very productive, a very forward-looking group of people that have come together and are always looking to engage new researchers and new ideas. That idea of having a unifying question that's broad enough to incorporate many different sub-disciplines, and I think has been very helpful to that event. The original founders of SAHRA, as well as the current management team now, has really tried to embrace researchers from a broad spectrum of universities, federal labs, as well as geographically diverse.
Okay, thanks. And so there's a question in the chat box from Henry Lynn. Do you see that?
Yeah. Any detailed or high-intensity soil mapping? No. Do you want to do it? Let's write a proposal.
There we go. 301.
Yeah, we have a question here. Ocean?
Picking up on the earlier question, I can speak loudly. What could you say about, I'm sure there are a lot of researchers, various people listening to this, who might benefit from your experience with having gone from not having worked with a large team of people to now working in this context. And CUAHSI, we're talking about very large groups of people working together. In what way has your perspective changed, or in what way would you see that an organization like CUAHSI, what are the things they would need to do in order to engage and bring people in so they would feel comfortable working in this kind of setting?
Ooh, I think that's somewhat difficult. I think CUAHSI does a pretty good job at that as it is, but I really think the key is the relationships that are developed between one or two investigators at a time. Just as you engage stakeholders most effectively by building trust, you engage other researchers by building trust. When you first see the behemoth of SAHRA, that 800-pound gorilla, like the 800-pound vegetation gorilla on the hydrology horizon, it may look like it's this uniform mass of individuals, but it's not. It's a collection of a lot of people who work reasonably well together, a lot of individual collaborations that grow over time.
Could I just, Jim Tuttle here. I think the key thing is the fact that nothing breeds success like success. And so the way I see it, what CUAHSI has to do is essentially to get in place some prototype activities, get some pathfinder activities in place over the next year or two. And if we can make those work, then you'll find people will want to join in the process.
Well, we do indeed see people wanting to join the process. Every time we present some of our preliminary results in one location or another, we have someone say, "Oh, it would be great if you did soil mapping. It would be great if you could do larger scale eddy simulation. We're constantly bringing in new partners in to work on different aspects of this. And that idea of success builds success hopefully will continue forward.
And it seems like most of you know, there was a joint competition for the observatory test beds, for lack of a better term, and those are about to be announced shortly. And so there's going to be several of those starting in short order. But your points are well taken. And so in the meantime, another few questions have come in. The first one by Dave Tarbotten is one that other groups have currently been wrestling with. And in terms of, you've been talking about how vegetation impacts hydrology, but what about the reverse? And do you want to say anything about how hydrology and topographic position influence the location and type of vegetation? And Dave, if you're out there, if you want to amplify this or clarify anything. But
okay, I see Dave's. Okay, here we go. Do you want to? All right, there we go. I can't fit the whole question on my screen. I would say that we look at it as a bi-directional. It's not just how vegetation impacts hydrology, it is how hydrology impacts vegetation. The quick and dirty summary of results that I showed lean towards the effects on hydrology because that's what we're charged to look at as a science and technology center. But the controlled burns, the sap flow work, the response vegetation and vapor pressure deficit, those are all our hydrologic, all our vegetation responses to the hydrology or the hydroclimatology. I think we view it as a bi-directional. We can't do this without a lot of ecology interacting with our hydrologic measurements. And then I see Kevin Dressler has a question. Any particular platform of instrumentation that may be used and transferred? I don't know about used and I don't know about transfer, but certainly used. I personally really like the idea of these ETRS arrays, where you try to close the water and energy budget at multiple domains. You don't black box the surface if you're doing subsurface, and you don't black box the subsurface if you're doing the surface. We operate on different time scales quite often, whether we're doing hydrometeorology, surface hydrology, or subsurface hydrology. But this concept of making sure you have measurements and you're not making assumptions about any of the particular constraints or forcings affecting your measurements at a larger scale, or mechanisms affecting your measurements and your observations at a smaller scale. That's one of the most important. And then I see David has another question about data and informatics. We have a huge and pretty successful database effort going forward here in SAHRA, where we're populating databases. There are two issues here. One is collecting the data that's out there that's generated by management agencies or other research groups and putting that into a database that's accessible to all. The harder issue is dealing with investigator-driven data. How do we get that into a database that's at some point applicable to all? That's the ongoing process, and I think it gets back to the trust of individuals working reasonably closely together. I don't think you can just create an institution and then say, give us your data and trust us to put it to the best possible uses. It's going to be an ongoing process. Henry Lynn, no, we can't, but we can get closer than by not looking at it at all. That would be my response to that question. The closer we can get to closing the balances in different scales, different locations, the better we can do at elucidating the important processes on different spatial and temporal scales.
As well as highlighting, what needs more R&D in terms of new instrumentation, new technologies. Any other questions on the phone? Or any questions on the phone?
Again, ladies and gentlemen, if you wish to ask a question, please key *1. No, sir, no questions on the phone.
Okay. Well, I've got the time being close to 4 o'clock, so I know some people are going to have to vacate the rooms that they're currently occupying. But I'd just like to, while we think of questions, Paul, I'd really like to take this time to thank you again for all of the work that you and your team, your large team, have put into this presentation. You know, you made a lot of great points, and I really appreciate it.
Oh, thank you. It's fun. And it's not my team. It is the team.
The team you're speaking on behalf of. That's appreciated. All right, folks, any other questions? Okay. Now I guess they're going to carry you away on a chair, Paul.
Or a rail.
All right, take care, everyone. Thanks a lot.
Thanks, John.